Just remember, it doesn't matter what I look like, you just want to follow what I do. Is it going? Okay, I'll start. Heavenly Father, we thank you for today. I thank you for seafarers visiting us. Just pray that you'd just be glorifying what we do here today. And we thank you again, Lord, for your many blessings to us each and every day. We thank you that you came to earth on human form and died for our sins. And we thank you that you give us righteousness if we just accept you to our heart, that we have forgiveness of sins that we certainly don't deserve, Lord. And we thank you for all these many blessings you give to us, Lord. In your name I pray. Amen. All right. So first things first, I think I'll owe you a proof, a little proposition. And here it is, the partial derivative with respect to x of a real valued function h of a function of two variables, f of xy, is equal to, well, we could denote it like this. We could say dh df times partial f partial x. Now this notation, what I mean by this is it's the derivative evaluated at f of x comma y is just, that's just another notation for that. And then partial f partial x is just taken at the point x comma y. Of course, if you write the point dependencies of everything, it gets to be kind of a drag, so I'm going to just stop there, all right? And so this is a chain rule. We used this yesterday to do some calculations, and I'll do some more examples here before too long. Tell you what, I'll even do an example before I do the proof. For example, if I wanted to calculate the partial derivative with respect to x of, say, I don't know, how about hyperbolic cosine of x squared plus x to the y. What I would do is I look at the outside function. It's like h of u is cosh of u, right? So what I have then is I've got sinh of the inside function, because the derivative of cosh is sinh. And then I have to do the partial derivative of the inside function. That's what the chain rule says. That's what we're going to prove here in just a second. All right, so what is that? So you got sinh of x squared plus x to the y power times, let's see here, 2x. And is that a power function or an exponential function in terms of x with y held constant? Yeah, this is a power function, so I use power rule. So this is plus yx to the y minus 1. There you go. So this rule we're using, the chain rule, we should take a second to try to show how to derive this, all right? So here's how it goes. Here's a proof. So let's see here, partial x of h of f of x comma y. All right. And let's see here. I'll do this at the point. I'm trying to remember if I need to put another point in here or not. I don't think so. So see, so definition of this, right, was what? It was basically we do the derivative with respect to time of what? H of f and basically replace x with x plus t, right? And then y just stays put at y, whatever y is, it stays there. And what do I do after the differentiation is done? I put t equals to 0, right? So again, the definition of partial derivative is you vary the variable that the partial derivative is taken with respect to, in this case x, and you leave the other ones alone, right? Leave y constant. That's what I've done there. So how do I calculate such a derivative? Well, so this is actually, h of a function, h of another function, right? I could call this thing some other name here, some name calling for you. Let's just call this thing phi of t for a second. All right. So what you've got is you've got d dt, or how about even better yet? Let's call it u. Right. So if I've got d dt of h of u, putting t equal to 0 at the end, how do you differentiate such a thing where u and h are functions of time, the real value functions of a real variable? This is the what? How do you differentiate a composite function? Chain rule, right? So I would do h prime of u times du dt. And after all that's done, I put t equals to 0, right? But just undoing the notation, what was u? All right, I got h prime of f of x plus t, comma y, and then d dt of f of x plus t, comma y. And then we take all this stuff and we put t equals to 0 after the end of it. T is a disposable variable we were using to calculate the partial derivative. Right. So what is that? If you evaluate the product of two things at time 0, it's the same as doing what? Evaluating the first one at time 0, and then evaluating the second one. I mean, this evaluation at time 0, you can easily see, you can just set things equal to 0, right? So the first thing I've got h prime of f of x comma y, right? Which is half of what we want, right? That's the dh/df term. That's h prime of f of xy, the derivative of the outside function evaluated at the inside function. And what's all this? What's that? It's u prime, that's true, but what is it? When we evaluate the derivative of f of x plus t comma y with respect to t, it's that by definition of partial derivative, this is what? X, right? This is partial f partial x. At the point xy if you want to get picky, but there it is. So there you have it, chain rule. Let's do some more examples. Sound good? Any questions about this though before I go on? How would you prove the product rule? If you wanted to prove the product rule. If I wanted to prove, for example, that partial y of f of x comma y times g of x comma y, right? Or as I usually just denote, partial y of f times g, what would I do? I want to prove that that's partial f partial y times g plus f partial g partial y. How would I do that? Let me not write it out. Let me just give you a sketch. Step number 1. Right, definition for partial y, right? That would be the limit, d dt of, f of what? X comma y plus t, g of x comma y plus t, evaluated at t equals to 0. Right? Step number 2, apply usual product rule from Calc 1. Step number 3, what would you do? Plug time equal to 0 in the appropriate things and identify the partial derivatives. So step number 3 is just collect the results and identify that, hey, there it is. That's the product rule, which is just what I did here. I put in the definition. I changed the notation so you could see what's going on here. We used the usual chain rule, and then we applied the definition again to conclude. The proof of the product rule will be just the same. So I'm not going to do that right now. If there are questions, if you try to work it out yourself and you can't make sense of it, you can ask me about it another day. Okay, sound good? So I leave that to you guys. So let's see, here's an example. This one maybe will take you back a little bit. Partial x of the integral from, let's say, e to the y to the sine of xy squared of, let's see here, how about f of t dt, where f is some function. Let's say it's continuous, so the integral makes sense. How would you do this? Yeah.
Do the fundamental theorems of calculus still apply with partial derivatives?
Indeed they do. Because the fundamental theorem of calculus, I mean, a partial derivative is just an ordinary derivative, right? Where we treat one of the variables as a constant. So yeah. So the fundamental theorem of calculus part 1 still applies. And the lower bound is a constant with respect to x, right? So this is actually just FTC part 1. Let me remind you what that said. It said d dx of the integral from, say, a to x of f of t dt is what? Just f of x, right? That was FTC1. Now this is not quite that because I don't have an x upstairs, right? So basically I have to think of combining the fundamental theorem of calculus part 1 with the chain rule. If instead of having x up here in calculus 1, if you have something else like, say, g of x, what happens? We get a g prime of x down here, actually. That's how it goes. So with that in mind, this derivative is f of the sine of xy squared, and then I have to multiply by the derivative with respect to x of sine of xy squared. No x dependence. So yeah. Now what's this work out to though? We have, looks to me like y squared cosine of xy squared times f of the sine of xy squared is the answer. And what I did there was to differentiating the sine, I used the chain rule again. But what's the derivative of the inside function there? Partial derivative of xy squared with respect to x is just y squared, right? That's where the y squared came from. You guys are starting to follow along? Yeah? Okay. Is this you don't know what I'm talking about here, do you? Some of you, right? Let me remind you how that goes. It's easily forgotten. What's the fundamental theorem of calculus part 2 say? It says the integral from a to b of what? Basically, f of u du is equal to f of b minus f of a, right? Where what? Oh, excuse me. Little f. And what is the relation between big F and little f? F is an antiderivative, right? If I differentiate big F, I get little f. This is commonly known as FTC part 2, right? Well, if you think about FTC part 2, right, and you allow a and b to be functions rather than just numbers, what do you get? A of x, right? B of x, f of u du is equal to f of b of x minus f of a of x. Now, how do I derive that? I derive that from applying the fundamental theorem of calculus to many times at each value of x. Right? But you can do that. What happens when you differentiate that? Differentiate with respect to x, right? Yeah. So I get d dx of the integral from a of x to b of x of f of u du equals to, on the one hand, I've got f prime, right? F prime of b of x But b of x is the inside function, right? So when I differentiate, I have to do the chain rule, and I have to multiply by db dx. And likewise, I get minus f prime of a of x times dA dx. But what is f prime? Little f, right? So as you can see, you can, in some sense, derive the fundamental theorem of calculus part 1 with the chain rule by just differentiating fundamental theorem of calculus part 2 in this way. When I teach calculus 1, I annoyingly call this third thing I found the fundamental theorem of calculus part 3. But this is actually what you need often to do the silly problems that they give you about differentiating integrals with variable bounds, right? What I just showed you is the tool you need for differentiating integrals with variable bounds. I used that here, right? I said f of the upper bound times the derivative of the upper bound. So for example, if I take partial y of the integral from e to the y to sine of xy squared, what do I get? I get f of sine of xy squared partial y of what? Well, the inside thing, right? Minus f of e to the y partial y of e to the y. A lot of Calculus 1 instructors don't actually come out to get to the point of saying this. You don't find this in books much. People try to make you use properties of integrals to do these problems rather than giving you this result. I don't know why. Maybe there's some reason. It's not been revealed to me. Let's see here, cosine of xy squared, and then chain rule says what? Times 2xy, yeah. Minus f of e to the y. And, oh, hey, that one I can do, e to the y. Okay, so there you go. Fundamental theorem of calculus, part 1 and part 2, still important to us this semester, by the way. They are ultimately the linchpin in some of the deeper theorems that we cover this semester. Okay, I owe you a example that's not using x and y. The notion of partial differentiation is not just stuck with letters like x and y, right? You can do other examples. For example, what if I have partial alpha of alpha squared plus beta squared? What would that be? The understanding here is that alpha and beta are independent variables. Okay. 2 what? Yeah, 2 alpha. Very good. Or what if I had partial p of p squared divided by 2m? Yeah, 2p. Oh, p over m. Yeah, 2's cancel, don't they? Very good. Yeah. How about partial m of p squared over 2m? Let's see, minus p squared over 2m squared, right? It's m to the minus 1. I mean, so we start with x and y because that's our familiar thing, right? But oftentimes in applications, you find other letters. No big deal. You can do it, right? Okay, so now that I've got us back into thinking about partial differentiation, I want to present to you a standard problem. Let f of x comma y equal to x squared y plus yx cubed, well, let's say y cubed times x. Find the maximum, minimum, and well, I'm missing a word. Find direction u hat in which f increases, well, excuse me, is, let's see here, let's say part A, increasing at maximum rate, B, decreasing at its maximum rate, or, you know, it's the most negative increasing rate, I suppose. I don't know, however you want to think about it. And then C, direction in which f stays constant. Now, this question is ambiguous until I tell you what. Yeah, I need to, well, it's up to us to find the direction. But we need to pick a point in order to make this investigation, right? So what point do you want to pick? 1, 1? I forbid the origin. The question does not entirely, well, I don't know. What is the origin? At the origin, it's not changing. Right at the origin, I mean, it's got a level point there. Partial x and partial y are both 0 there, so it's kind of constant in both directions at the origin. So let's say, consider the point. I'll almost take your suggestion. I'm going to take 1 minus 1 so we can see at least a little bit of contrast, although I do like the number 1. So how do you figure out how a function is changing at a point? What is the tool to do to investigate that with? Derivatives, right? So the tool we're going to use is the directional derivative. And we're going to let u equal to ab. Since we don't know it, we'll let it be variable, right? And since f is continuously differentiable, what does it mean to be continuously differentiable? I haven't talked about that in here yet, I don't think. Continuous differentiability of a function means that the partial derivatives not only exist at the point, but they're continuous near the point in question. When the partial derivatives are not continuous as functions of several variables, this all breaks down. And there are sick examples that show you what our current methodology fails. So continuity of the partial derivatives is important if we're going to apply the standard tool set. But this is a continuously differentiable function because what are the partial derivatives here? fx is equal to what? Fy is equal to what? 2xy plus y cubed, and what? X squared plus 3xy squared, right? Those are polynomials. Those are continuous. We have the necessary ingredients to use this. So the directional derivative in the u hat direction of f at the point 1 minus 1 is equal to, this is a theorem, it's the gradient of f. Take the gradient of f, you evaluate at the point 1 minus 1, and you take the dot product with u hat, which in our notation is ab, okay? I guess I could have written u hat, whatever. So what's the gradient vector, remember? fx, fy, right? So what I got to do is I got to plug in the point into our formula for the gradient vector. Hopefully I have not inadvertently chosen a point where it's 0. If the gradient vector is 0, we'd have to think about it some more. Well, anyway, I mean, that just means that the function's locally constant if the gradient's 0. But, so I guess you could say it's minimized and maximized in every direction, but that's kind of annoying. Okay, so plug in 1 minus 1, what do we get here? 2 times 1 times minus 1 minus 2. Minus 2 minus 2 plus minus 1 cubed is what? Minus 3. How about the other one? So you plug in 1 and minus 1, what do we get? 1 squared. Minus 1 squared. Everything's positive this time around. So I get 1 plus 3. I think I get 4. Right? And so the rate of change in the AB direction is minus 3A plus 4B. Now, what I advertise to you is to answer this question, we can think geometrically. You see, because generically speaking, the directional derivative in the u-hat direction of f at a point P, here's a generic truth for you. If that's the gradient of f at the point P, dotted with u-hat, we can replace this with the magnitude of the gradient of f at the point P, right, times the cosine of the angle between, if I picture, here's my point P, and if I picture, here's gradient of f, right, and here's u, and this is the angle between them, that's a formula for the directional derivative, right? So if you want to get the largest possible value, you pick theta equal to 0. If you want to get the largest possible negative value, the largest rate of decrease, you pick theta equal to 180 degrees, right? And if you want the direction along which the function stays constant, you pick 90 degrees. Or minus 90 degrees, if you want to think of it. Right? So, how do we figure that out? I mean, we already have right here that the gradient of f, right, at our point is 3, 4, right? Yeah, and the length of that, in fact, the length of the gradient, you just told me is 5. It's square root of 25, right? So, which we recognize as 5. Yeah, so this function increases at a rate of 5.
What's the gradient? Negative 3, 4?
Oh, thank you. That matters, so. So the answer to 1, or rather part A, is it increases at rate 5 in the, let's see here, minus 3/5, 4/5 direction. I'm giving the direction as a unit vector, right? Now you could restate it in terms of standard angle. What standard angle is that vector at? Do you guys know? It's between 90 and 180, right? I don't know off the top of my head, but if you got a calculator, you can figure it out. Let's see here, B, it's decreasing at rate, well, and here's where the language gets a little, I mean, I could say it's increasing at a rate of minus 5, I suppose, but let's say it's decreasing at rate 5 in the 3, 5, minus 4, 5 direction, right? The opposite direction is the direction it decreases. And then where is it staying constant? When they're both positive? No, it's not quite it. You need a vector that's dot product is 0. Let me show you guys a trick. For two-dimensional vectors, you can always create another vector which is perpendicular to the given one as follows. If I'm looking at the vector AB, right, and I want something, if I want V perpendicular to AB, here's what I do. I just go, all right, I think for a second, and then this pops into my head. Or, depending on the day, this pops into my head. Anyway, these are rotations either by plus or minus 90 degrees. It's the two-dimensional analog of the cross product. It's how to create a perpendicular vector given a vector. So if I want a perpendicular vector to this direction, I just switch them and put a minus. So minus 4/5 and 3/5. So I actually, tell you what, I'll put the minus off the 4/5, so that'll do. So he was almost right. Just we had to flip them in addition to get rid of the minus, which may have been what he was saying to start with anyway. I often misread what students say on the fly. So 4/5, 3/5 direction. Because that dot product with the dot product of that with the gradient is 0. So that's at 90 degrees. If you take this vector, 4/5, 3/5, and you put it back up in here, the dot product gives you 0. The rate of change is 0. When the rate of change is 0, it's constant in that direction. ¿Es bueno? A question? What if I was to ask you something nastier? These are easy. Here's something unpleasant. In which direction does f change at rate 4? At the point 1 minus 1. Now, I can, before we solve this one, there's an easier question I could ask, right? I could say, in which direction does the function change at rate 6? That's an easy question. It can't change at rate 6. The maximum rate of change that's allowed is given by the magnitude of the gradient vector. So if I asked you at which direction it was changing at rate 6, you'd be like, oh, fine. Aha, easy. It's impossible. There's no direction, right? And in fact, you wouldn't need to do a lot of calculation to figure that out. When you're working one of these problems, the first thing you should do, especially if it's open-ended, is to calculate the magnitude of the gradient vector at the point in question, right? Because that gives you a sense of what's possible. All right, but this, rate 4, right? So how do you solve this? We'd have to solve minus 3a plus 4b, right? That's the, oh, by the way, guys, I should mention, a lot of engineering books use the following notation. This will also be called partial f, partial u hat at the point P. Because that's really what it is. You're taking the partial derivative of f in the u direction. Going back, so this equal to 4 anyway is what we're after. You're like, but that's a lot. You can't solve that equation, right? I can graph it in the AB plane, right? What is that? That's b equals to what?
1 minus 3/4.
Almost agree. 1 plus 3/4, say, right?
Yeah.
So y-intercept is 1. And the slope's 3/4. I don't know. It looks something like, roughly speaking, like that. Whatever. You're like, well, that's not. That you can't. That there's infinitely many solutions, right? If that's all that there is. But is that all that there is? In calculus 3, we insist that the directional derivative be calculated with respect to a unit vector, so that there's a standard rate of change with which we can discuss amongst each other. So we also know something about AB. It's a unit vector. What does that say about the relation of A and B? Yeah. And A squared plus B squared equals to 1. What's that look like in the AB plane? Indeed. So, that happens to, look, there's one easy solution. That's fortunate. My picture is not necessarily correct. I'm just saying if the gradient is not too small, the line will intersect the circle at 2 points. That's generically going to happen. One of them you can already see. One solution is what? Yeah, a equals 0, b equals 1. That's one direction. So one, if you're at the point 1 minus 1 and you want to go in a direction, if you want to look at a direction on the graph z equals f of xy in which you're increasing at rate 4, you could go in the direction of the y-axis. Right. Remember geometrically, we can always think about what we're doing as looking at z equals f of xy, right? So there's a graph, you know? And so one way to think about the gradient, if I pick the point, you know, over the point P here, then the gradient vector, it will point in the direction in which the graph is going up the steepest rate. Yeah.
How do we know?
Our assumption with the unit vector u had is it's a unit vector. So it has to have length 1. So this is the condition that the unit vector AB have length 1. Okay, so, well, what's the other solution then? How do you solve this? I mean, that we just got lucky from the graph, right? That's an accident. So generically speaking, you have this equation and this equation. You can solve it, right? You just solve for one of them. Oh, here I already solved for b. So we've got a squared plus 1 plus 3/4 a quantity squared equals to 1. And you got to solve that. Now what's that give us? A squared plus 1 plus 6/4 a plus 9/16 a squared is equal to 1. The 1's cancel. And you got 25/16 a squared plus 6/4 a is equal to 0. So a times 25 over 16 a plus 6/4 is equal to 0. So I can see the other solution that I haven't found yet is when 25 times a over 16 plus 6/4 is equal to 0, whatever that is. I know I could simplify these, but I'm just keeping them the same so you can read what I'm doing faster. What is this? Minus 24 over 25, yeah? Then what's the b? Sorry, it's not that I don't trust you. It's just I have to think through it here for a second. So that looks to me like 28 over 100. Me? So put all this together. The other direction would be minus 24 over 25, comma. Oh, that's, yeah, 7. Okay, great. So either that direction or this direction. These both, you know, say f changes at rate 4, you know, at the point 1 minus 1. Okay? It takes me a while to work one of these out in all of its glory. But if you're just working it by yourself, it's really not that hard of a problem. A lot of times the problem you'll find in the book or my homework, it might be more specific. I might just say find the rate of the change of the function at a given point in a given direction, right? Sometimes we ask that question, so you don't have the trouble of finding the AB and searching for it. You're given the direction and asked the rate of change. I mean, there's a lot of variations on this problem. Is good? All right, so we'll be studying the relation between the geometry of the graph and the gradient vector more in future lectures, but I want to transition now to three variables. How do you do 3 variables? Or n variables, why not? So the formal definition is the same as the one I've written down. And I think I've written enough formal definitions today. I'm not going to write another one. I'm just going to show you some examples, all right? So partial derivatives in 3 or more variables. How's that go? Here we go. Partial x of x squared plus y squared plus z squared. Indeed, this is 2x. And if you let me give this a name, let me call this thing w. All right. So, in other words, I just calculated partial xw is equal to 2x. Sometimes this is a convenient notation for partial differentiation. Just instead of writing partial x, you can just write partial sub x. It expresses the same operation with a little bit less writing. I found that to be a very useful notation over the years. So let's see here. What's partial y of w? 2y, yeah. And partial z of w? Same, okay, same. I like that answer. Very good, very good. So you're like, that was boring. Give me a more interesting example. Fine, I hear you. Partial x of x to the y to the z. That seems more annoying, yes? What kind of function is this in terms of x? So when we partial, sorry, I just, words. Y and z are constants in this differentiation, right? So this is actually a power function, is my point. Was that your, okay. Yeah. Y to the z times x to the y to the z minus 1. Yeah. Font size becomes an important thing here, yeah. What if I had partial y of that same thing? It's neither an exponential function nor a power function now. The answer right now, the responsible answer to give you is on a later date. I could show you how to do it right now, but technically speaking, there are some techniques we're supposed to talk about before I do that example. Yes, sir? It's multivariate implicit differentiation, yes. But this one we can do. So I'll do this one. See, now what you're looking at, let me just reemphasize what this is partial z of x to the y, parentheses to the z, right? That's what that means, that notation over here. So you see the base is x to the y, right, which is a constant with respect to the z differentiation. So this is now an exponential function in z, right? So I do natural log of x to the y times x to the y to the z. And of course, you could simplify that, and you could pull the y outside the natural log and junk, but there it is. What's the graph of a function of 3 variables look like? I mean, I pictured over here z is equal to f of xy. You notice z here is the, what would partial z partial x be over here in this context? What's partial z partial y? What does that mean in this context? It means you partial differentiate the function, right? So this is partial f partial x, right? And this is partial f partial y. In these examples over here, what's partial z partial x? It's 0, right? Because over here, we're taking x, y, and z to be independent. You're like, but wait a minute, is z a dependent variable or is z an independent variable? Yes. Yes, it is. Okay, so context matters. Directional derivative. What's the directional derivative look like from functions of 3 variables? The directional derivative in the u hat direction of f at the point P is equal to the gradient of f at the point P dotted with u hat. You're like, you already told me that. I know I did. I guess what I didn't tell you is that formula is good in n dimensions, with the understanding that this thing, the gradient, is generically speaking, in general, partial 1f, partial 2f, partial nf. Sorry, I got carried away. I figured why do 3 when I can do n? Of course, the direct visualization of what's going on starts to be harder. I can't talk about graphs anymore because I'm talking about a function of more than 2 variables, right? If I was to try to look at w of f of x, y, z, what would that be? The collection of all such 4 tuples. I mean, you could do that. You could look at the graph of f, which would be, x, y, z, and w, such that w is equal to f of x, y, z. That would be the graph of f of 3 variables. You could do that. It's allowed. But, I don't know, maybe you can visualize it. I personally can't. I mean, there are techniques I can use to understand aspects of it, but direct visualization in 4 dimensions is not something it's not one of the rights and privileges endowed to me by my creator. It's not something I can do. But we can still calculate directional derivatives. And we can also understand functions of 3 variables in other ways. Like, you've already been looking at them. On your test, I already asked you about it, right? How about this? X squared plus y squared plus z squared equals to 1. What's that? That is a sphere of radius 1. And you know what happens when you take the gradient of this? Call this thing f. You get 2x, 2y, 2z, right? You know what that does? If you plug a point in on the sphere, that points in the direction in which you find the next sphere, the next level up. It points directly away from the surface of the sphere. That's the geometric meaning of the gradient. But now I'm getting into a future lecture, so I'll shut up. Have a good weekend. Sorry, Mr. Vu. No epsilon and deltas for you. Hey, it rhymes. He's trying to get me to do epsilon deltas today. Do you want me to do epsilon deltas? I mean,